What in the world is this picture? Stick around and we will not only find out what it is, but more importantly, what it is used for. Welcome everyone. I am a science nerd covering the joys of quantum mechanics, and in today's video, we will discuss the Laguerre polynomials. By the end of this video, you will be able to calculate these Laguerre polynomials and use them to construct the associated Laguerre functions for a particular level of n and L. And of course, we need to understand why we need these polynomials and their not so distant cousins, which I have a funny for you at the end. Plot and interpret the graphs and understand their relevance to the hydrogen wave function. So pretty fun setup here. Let's go ahead and dive into what we're tasked with. In this question, we are trying to use the equations given and calculate these in more of a generating function method. So we want to use the equations of 4.88 and work out the first four Laguerre polynomials. And then in part B, we wish to use the equation 4.86, 4.87, and 8 to find v of p, which is the polynomial of interest that we need the associated Laguerre function for. And then C, we wish to find v of rho, again, for the same case, but this time we want to use the recursion relation. So, we've done that before in 2 questions ago, I believe. I'll link that below so you have it. But, the goal here is we have to use some new methods to find it, and we'll have a new appreciation for what our computers can do after the fact. Before we begin, though, I would like to mention that there's a free companion PDF that you can use to follow along, which I assure you will definitely want for this question. The link is below. In part A, then, we are tasked with finding the first 4 Laguerre polynomials. And based on the equations that we have in the book or the PDF, we have LQ of x is equivalent to e to the x over q factorial with the dx to the q order, and we have e to the minus x q to the, x to the q. All of this is saying that these derivatives are acting as a generating function for the specific weight, and in this case, the weight is the e to the negative x because we know derivatives don't affect it. All it does is alternate the sign due to the negative coming down from the chain rule. And this is much to the same style of generating that the Legendre polynomials had and the Hermite with the Rodriguez formula, right? So all of these things are actually symbolically linked together with the different weighting function for their generating functions. Pretty cool to see come together. But without further ado, if we want the first 4, that means we need q from 0 to 3. And our 0th order is the easiest one because we see we have 0 factorial, a 0 derivative, and x to the 0. Well, easy enough to deal with. We have e to the x here and then an e to the negative x that survive, but notice the color code in red. They go to e to the x minus x when we multiply the exponentials, and that goes to e to the 0, which goes to 1, and all that other fancy algebra. Not too bad there. Pretty expected. That's also a convention, by the way, to set this L0 equal to 1 if you read a little more into it. But now on to the 2nd order, or the qth order for q equal 1, where we have a little more work to do now that we have a derivative that survives. So the factorial, easy enough. You can look at the PDF for simplifying. But here we're noticing that we have a product rule here, and now that's where the chain rule effect comes in, and we drop down to negative, leave the x alone. Derivative of the x goes to 1, leave the exponential alone. Again, the weight is made perfectly to where when you factor it out after the derivatives, the e's cancel. That's why we have a plus x here and a minus x there. Pretty darn clever. Nonetheless, what's left over is a 1 minus x. So pretty cool. Let's continue on the momentum train then. Moving on to q equals 2 then, the 3rd polynomial. When we plug it all in, we have a little more spicy derivative because we have to take it twice. Noticing that our polynomial now is e to the negative x and x squared. So whenever we move this on, we're going to have a product rule and then factor in some chain rules. Once we simplify the first derivative and factor out the e to the minus x, we see that we have a 2x that comes from this polynomial and then the minus sign that comes from the exponential. And you can see how this keeps generating a polynomial for however many derivatives we had. Notice last time all we had left over was a 1 and an x. This time we're a higher degree. So again, pretty clever construction here. So once more, we take another derivative, and you see we factor it out after we clean it up. The product rule leaves us with a new polynomial of 2 minus 4x plus x squared. Factor these exponentials out, let the x's cancel to 0, so the exponential goes to 1. Cool. And then if we either factor out a 2 from every term or distribute that 1/2, however you want to look at it, what we see is that we end up with a polynomial of degree 2. Makes sense, L equals 2. And we have the coefficients of 1, -2, and 1/2. So this will look interesting when we graph it. Let's finalize this first part and get L3. With that then, what we have is 3 factorial in the bottom, 3 derivatives to take. Oh, and we have a cubic x here. So let's go ahead and be careful, follow the same line of thought and factor out the e to the negative x after every turn. We see that we have a new term here coming from the chain rule and product rule. And then once again, another polynomial extension with the 6x. And once again, another polynomial extension with the 6. Pretty clever, pretty clever. I can't get over how clever this is. But with that being said, we, do the e to the x, negative x trick, and then factor out a 6, cancel away, and we see we get our condensed polynomial here. So that was a lot of moving parts, and the PDF has all the little nitty-gritties on that. But let's go ahead and summarize this in a nice, neat table. Finally. Now we could start to see how these Laguerre polynomials start going and constructing themselves as we go up in order. And so you see 0, 1, 2, 3, and you see we just keep tagging along, tagging along, tagging along, alternating signs. And you remember that whenever we had the last set of in spherical harmonics, we had -1 to the n power. Now this is where that's starting to come from because of these generating functions. Pretty clever, I must admit. Nonetheless, let's go ahead and see what is funny about this setup. When I asked an AI prompt to compare the Hermite, Legendre, and Laguerre polynomials, I was expecting something like a chart comparing the tables because that's what happens when you Google it, but instead we actually get a pretty nice funny. Apparently, AI and the rest of the internet thinks that they're all cousins, and they just change colors from one thing to the next. As you see, they were trying to put Hermite, that looks like Legendre, and then Laguerre polynomials here, and they must be going up the stairway to some mathematical convergence. But nonetheless, I found that pretty cool to see how the AI thought of these things. So let's move on and move to part B, where we can actually construct something physical and get a result. All right, well, that was a quick transition. Here we want v of rho, which if we recall, this was the polynomial that occurred when we took away the asymptotic parts of the solution to the radial wave equation. Right? So this is what happens in any of the intermediate stuff that's not a really big rho and a really small rho where we blow up at either end. The exponential dampens us. The rho to the nth power keeps us stable and when we get really small. So here then what we have is the case where everything else comes in between. So all the weird nodal lines we saw last question. This is where some of those things come from. And to get there, we define that the nu of rho comes from the associated Laguerre polynomial or Laguerre function. This thing uses the Laguerre polynomial, as we could tell in the formula for it, and it does so in a recursive way. But what this does is it tells us for a particular state up here, where we had, this is also up to m because we had 2 to the L plus 1 choices to have for these quantum systems. And then here is our order factor that we saw with the recursion relation. This is the highest degree possible, was n minus L minus 1, and that keeps the asymptotic form together. So when we condense that, notice here that we have a single row, here we have 2, so we have to be careful in our construction, just like we had to for the spherical harmonics. Nonetheless, what we're actually looking for is L to the 5 and L2, with again being associated or evaluated at 2 row. What this form here, this association, tells us is that we actually need the Laguerre polynomial of 5 plus 2, and then we have to retake 5 derivatives of it. So this is going to be a long, tedious task, and this is where I am, encourage you to go look at the PDF, because it is not worth chugging out every single derivative. That is what, 12 derivatives total. It's just not worth it. But you can see the copy paste work in there and get all the nitty detail you want. The big thing here to notice is that for this, we had to read the form n equal 5, L equal 2. That led us to a Laguerre polynomial of 7. That is what's used to determine the polynomial that we need for the radial wave function. So let's get to calculating. Okay, so as promised, I'm not going to put all those derivatives in here, but they are accessible to you. What we need to find out is that from plugging the 7 into the form for this Laguerre generating function, we get a 7th degree polynomial as expected. And here are the degrees with their coefficients. I would like to point out now that this needs to be differentiated 5 times, okay, which is summarized here with the nu of rho equation. And so what we're going to use here is a Leibniz trick, and which we kind of already had from a sense of calculus. If I have to take a higher degree derivative than what I have in my degree of the polynomial, it goes to 0. So if I need to take the second derivative of x, I know that my first derivative leads me to a constant, my second leads me to 0. So that is the generalized form there, and we could see that if with this 5 here, everything that is less than 5 in the polynomial gets truncated and gets cropped out to 0. So we're not going to have to worry about that. It is in the PDF, but I'm just alerting you to the fact that this is used heavily because no one wants to sit there and chug out derivative after derivative. So be aware, Leibniz and others use a trick for this. And then more importantly, they actually generated a binomial expansion for how these things were uniting based on these derivative generating coefficients. Nonetheless, let's go ahead and tidy this up and get our associated Laguerre function. All right, so now that we get all the derivatives done, again, we see that 5, we would have to bring the degree for x to the 5th down 5 times. So 5 times 4 times 3 times 2 times 1, that's 5 factorial. And in a similar manner, we do that 6 times, so 6 to 1 here, and then 7 to 2 here, so, or 7 to 3 here. So our coefficients reduce quite a bit, as you probably would have expected. We can't go from one crazy, big polynomial to a second degree correction because of L equals 2. So nonetheless, let's go ahead and see now that when we evaluate this polynomial at x equals 2 rho, we get 21 because the negative signs cancel. Fair enough. We get a negative 7 times 2 rho. Okay. And then here we have 1/2. Be careful with the squares because the square belongs on the outside. You're plugging 2 rho directly inside the parentheses. So that means you have to square the 2 and the rho. And if you square the 2, that gives you a 4, which cancels with the 1/2 to a 2 right here. But this is our actual radial polynomial solution for the non-asymptotic forms, which we again calculated a couple questions ago using a recursion relation. And so what we're going to do now is segue to that recursion relation to verify this. So again, in part C then, we had n equals 5 and L equals 2. And the highest degree that we could have was n minus L minus 1. Same thing that we saw in the Laguerre associated function in the subscript there. This is how they stay consistent. All right, so let's go ahead and evaluate this with the recursion relation. We notice that we could tidy this relation up because of the values of 2 from L and the value of 5 from N. So we just have something that we have to look at the cases for. So J minus 2, J plus 1, J plus 6, all that fun stuff. We've seen this before. What we notice is that the polynomial has to go up to degree 2, so that means J equals 0, 1, and 2. So let's go ahead and plug those in. To find C1, we plug in J equals 0, simplify down, not too bad. Negative 2/3 C0 is what we come up with. If we plug in J equals 1, we get C2. And again, we need to simplify down. Note though that here I have a C1, so I need to substitute in our previous results into this C1 in order to find out my C2 in terms of C0. That way I have one variable. Let's do that now. Wonderful, wonderful. So when we do that, we get a whole host of cancellations. This comes from the fraction recursion relation from plugging in the J term. We see that the 2 cancels. We have a negative cancel from the substitution of the coefficient. And we get our final simplification of the expression to 2 over 21 C0. Not too bad there. And then finally, we get our nice check here for if we plug in J equals 2, the series terminates and I get a 0. And this would work for J equals 3 because then I would plug in, for C4, I would plug in C3 equals 0 and I would get 0. So we just keep getting zeros. This is that truncation term. So if you're ever plotting these things online and you get an error, that's probably why. Nonetheless, what we see is when we compose the polynomial, we get this thing here. Wonderful, wonderful. But the one disadvantage to this is that we're going to have to normalize this with the radial integrals or radial integral, singular, to find out what the C0 is. Versus what happened with the Laguerre stuff, that gave us all the polynomials where we didn't have to worry about it, or the coefficients where we didn't have to worry about it. We assumed it was normalized due to the first term being 1, and so on and so forth. So there's trade-offs, of course, but I think the recursion relation is a little bit easier to deal with, but that's just me. Nonetheless, the easiest way to actually do this is to let the calculator or the coefficients, the computer calculate all of these for you. So that'll be the quickest way out, and I will see or upload a picture for you now, and see you at the next one. All right, so there we go. Not sure why these didn't load previously, but let's check it out. So here we have on the left-hand side the Laguerre polynomial, which is what I teased you with to begin with. And then, of course, the generalized Laguerre polynomials in the form that we want. Notice that they kind of look chaotic and crazy and just all over the place. Yeah, that's just crazy. What I want to draw attention to is the fact that these, once we normalize them, turn into the radial part of the wave equation. And so that's what we saw when we graphed it a few questions ago. And these are all the Laguerre polynomials that we had to calculate. Well, up to 3, and then of course we had to calculate up to 7. And you see that you can kind of look like they're expanding in powers, which makes sense. We have the linear line here, straight line down because of 1 minus x. Then we curve up into a square polynomial because of the x squared here for level 2. Level 3, of course, we have a cubic facing down. So it's really cool to see these come together. On the other hand, for the associated Laguerre polynomials or Laguerre functions, we have a stable state of quadratic polynomials, which is indicated by the subscript 2. Okay, remember that subscript 2, just like we see here on the green, that is a polynomial of degree 2, so a quadratic makes sense. The importance here is that the different levels for L give us different varying shift factors because of the coefficients that we have with the minus signs coming in, and the of course the powers that we can divide by or multiply by in the derivative. So all we're doing is shifting these, and that's pretty cool. But our approximating function was a second degree, so it's nice to see that this is at least consistent. This is all done in Python. It, took a little while, but that's just tinkering with the aesthetics. I think that having a computer do this for you is going to save you a much greater deal of headache than trying to calculate them yourself. Feel free to reach out because Python's used everywhere. But nonetheless, now we see what they are, how they form, and the restrictions they're in, and how to read it. So be on the lookout for them whenever you see hydrogen. Well, that was really fun. Thank you for watching. To summarize, we covered how to construct the Laguerre polynomials, using the polynomials to construct the associated Laguerre polynomials. That was a long task. En route to understanding the hydrogen atom, because we need this for the radial part. And then, of course, we looked at the graphs of these and were able to interpret what they were telling us based on the levels that were allowed, including where you might get computational errors. So be on the lookout for that. These are messy and best done using a computer. I think I can show you the PDF and you will agree with that. So just be careful on the restrictions again for N and L. That will come in and either harm you or save you a headache. Either way, you have to understand it. If you enjoyed this, please consider supporting this channel by subscribing and sharing this curiosity. Books, notes, and other reference material is found below. If you have any questions, please feel free to reach out here or at the other links below. Probably Instagram would be the easiest. As always, thank you for watching, and until next time, stay curious and happy learning.